Reflection is when waves bounce off an object. Sound waves are reflected by hard, flat surfaces and is why we get echoes. You hear a delay between the original sound and the echo, because the echoed sound waves have to travel twice as far to reach your ears. Smooth surfaces like glass or polished metal reflect light in a regular way, so a reflection can be seen, like a mirror, or seeing your face in a calm pond. When sound and light waves pass across a boundary between two substances, like air and glass, they change speed. This is because the substances have different densities. The change in speed causes the waves to change direction, which is known as refraction. Because of refraction, things in water look closer than they really are. Water appears shallower than it really is. And a straw in a glass of water looks like it bends at the surface, because the refracted light wavelengths make you think the straw is in a different place to where it actually is. When waves meet a gap in a barrier, they pass through the gap. They then spread back out after they pass through the gap. This is diffraction. The way the waves respread depends upon how big the gap is compared to the incoming wavelengths. We have diffraction to thank for loudspeakers.
When there are two disturbances near one another and their respective series of waves overlap, this is called an interference pattern, and we can see how the regions where the waves intersect generate a completely new pattern. This is easy to see with waves in the water, but sound and light waves also do this. There are a few different things that can happen when interference occurs. Say two individual wave pulses are traveling towards each other, and they have the same amplitude. When these meet, the amplitudes at each point will be added together to produce the respective points on the resultant wave. So there will be a moment where there is one wave with twice the amplitude. Then the two waves continue in the direction they were moving in. Each wave maintains its own characteristics before and after the interference. When a resultant wave has greater amplitude than the individual waves, like this case, this is called constructive interference. Now let's say the pulses are on opposite sides of the equilibrium position. Again, according to the superposition principle, we will add the amplitudes to get the resultant wave. But in this case, the two amplitudes add to zero, so the resultant wave will be as though there is no wave at all. Then the waves continue along their trajectories. This kind of interference, where the resultant wave has a smaller amplitude than the individual waves, is called destructive interference. And if the resultant wave has an amplitude of zero, like this example, it is called complete destructive interference. This concept applies to periodic waves as well. First, we can consider two sine waves that are precisely aligned. They are said to be exactly in phase. We can add the amplitudes at every single point, and the result is a similar looking wave with twice the amplitude, due to constructive interference, because the crests align with the crests and the troughs align with the troughs. But then, if we shift one of these by half its wavelength, now the crests of one align with the troughs of another, and at every single point on the x-axis, these waves will add up to zero. They are said to be exactly out of phase, and this will be an example of complete destructive interference. This is what noise cancellation headphones do. Small microphones detect background noise and process the associated signal, and then reproduce this noise in a way that is precisely out of phase with the signal. The resulting destructive interference results in zero, or at least dramatically reduced sound waves reaching your ears.
In summary, all types of waves, such as light, sound, or water waves, can undergo the phenomena of reflection, refraction, diffraction, and interference.